today I am going to discuss some applications of the intermediate value theorem. Firstly, we can talk about applications in nature, and so we might ask ourselves, where do continuous functions occur in nature? Now, one important fact in physics is that if you have a particle, a physical particle with some mass, then its position as a function of time will always be a continuous function. So, if I call its position a vector r at say time t, rt, we could write it as the vector xt, comma yt, comma zt. So, x, y, z are the coordinates of the particle at time t, then x, y, z, these are continuous functions. More interestingly, if this is the position, if RT is the position of some rigid body, it is the position of its center of mass at time t, then x, y and z are continuous functions. Suppose you have a plane P given by the equation ax plus by plus cz is equal to d. Then what we can say is that if the center of mass is on one side of the plane at time t equals 0, and on the other at time t equals 1, then there is some time in between 0 and 1 such that r of t naught is actually in the plane. This is a simple application of the intermediate value theorem. We can actually write a mathematical proof of it. Consider the function f of t to be, now remember what was the equation of the plane, ax plus by plus cz. So, let us just take a times xt plus b times yt plus c times zt, and this is equal to d when you are on the plane. Let us just subtract d. So, when you are on the plane, this equation, this right hand side is equal to 0, and when on one side of the plane ax plus by plus cz is positive and on the other side it is negative. So, you can conclude that f, firstly it is a continuous function because it is a sum of 3 continuous functions multiplied by constant functions. So, f is a continuous function. So, f from 0 1 to r is a continuous function. It has opposite signs at t equals 0 and at t equals 1. And so, by the intermediate value theorem, there exists a point t0 strictly between 0 and 1 such that f of t0 is equal to 0. But if f of t0 is equal to 0, this is the same as saying that r of t0 is a point in the plane P. Now, let us look at a somewhat geometric consequence of the intermediate value theorem. So, suppose I have some sort of shape. So, in this case I will draw a heart, let us call it H, and let us say that the area of this heart is 1. Okay, so if I had actually drawn a perfect heart which was symmetric, then you would not be surprised if I told you that if I were to just take a vertical line through the center, it would divide this heart into exactly 2 equal parts in terms of area. So, the area to the left of this blue line would be the same as the area to the right of the blue line. But what if the line I am taking is not vertical, but at some funny angle? So, here I have drawn a line at some funny angle, and can I move it parallel to itself so that at some point it will divide this heart H into exactly 2 equal parts. So, again this is something that can be proved using the intermediate value theorem. So, let us say this line is given by the equation Ax plus By is equal to t, where t is some parameter that I will vary. So, as I vary t, this line Ax plus By equals t moves parallel to itself, because after all its slope is a over b, right. Yeah, its slope is a over b, and so this line will move with the same slope, it will move across this heart shaped region. So, let us set up a function here. Let f of t be the function whose value at t is the area of the region x comma y in H, such that alpha x plus beta y is less than or equal to t. So, now I would move this line, maybe to start off it is here on the left side of this heart, and to end with it is somewhere here. So, now if you look at the first line on the left, the entire region H is to the right of this line, and once you move this line from here all the way to the right, the entire region is to the left of this line. And so, what you can show is that there are constants m and n such that for t less than or equal to m, f of t is equal to 0. The entire area is to the right of the line, and for t greater than or equal to n, f of t is equal to the area of H, which is 1. And so, by the intermediate value theorem, there exists a t in the interval m comma n such that f of t is equal to half. Now, let us look at an example of a more mathematical nature. So, the theorem here is that any polynomial with real coefficients of odd degree has a root. So, what I am saying is that if you have a polynomial f of x which is of the form a n x to the n plus a n minus 1 x to the n minus 1 plus a 1 x plus a 0, and we will assume that has degree n. So, a n is not equal to 0 and this n is odd. What I am saying is there exists x naught belonging to R such that f of x naught is equal to 0. So, let us give a proof of this statement. The idea behind the proof is that if you have a polynomial of odd degree, then if you take x to be very negative, very much to the left of 0 on the number line, or if you take x very much to the right of 0 on the number line, the signs of f of x will be opposite. To see this, so there are two cases. So, if a n is positive, then to the right of the real line, the values of f will be positive, and if a n is negative, then it will be very far to the left of the real line, that the values of f will be positive. Let us just assume for the moment that a n is positive. Okay, I will write this polynomial somewhat cleverly in the following form. F of x can be written as a n times x to the n. Now, this for large n will be the biggest contributor to the value of the polynomial, and the rest I will write it like this. So, this 1 comes, I am taking this a n x to the n out. So, I will get a n minus 1 by a n x inverse plus a n minus 2 by a n x to the power minus 2 plus a 0 by a n x to the power minus n. So, what I am going to try to do is make each of these terms very small by choosing x to be large. So, let us do some rough work here. So, I want a n minus I divided by a n x to the power minus I. I want this, I am going to try to make this less than, say, well, there are n of these terms. So, if I make each of them strictly less than 1 by n, then their sum in absolute value will be strictly less than 1 and can never cancel out this 1 up here. So, if I want this, then what I can do is I can make sure that a n minus I by a n times this. So, I can just make sure that absolute value of x to the minus I is greater than n times a n minus I by a n. But I want this to be independent of I. So, if I take the absolute value of x to be greater than 1, then the absolute value of x to the minus I will be strictly less than the absolute value of x. So, now what I can do is, for absolute value of x greater than the largest of 1 and n times absolute value of a n minus I by a n, I goes from 1 to n, I will have absolute value of a I by a n x inverse is less than 1 over n. And so, what I get is that 1 plus a n minus 1 by a n x inverse plus a naught by a n x to the minus n. Well, this is greater than or equal to 1 minus the absolute value of a n minus 1 by a n x inverse minus the absolute value of a 0 by a n x to the minus n, but each of these absolute values is less than 1 over n. So, this whole difference will be greater than 1 minus n into 1 over n, which is equal to 0. And so, this part inside parentheses up here, this is always going to be greater than 0 if the absolute value of x is greater than this maximum, which let us give it a name, let us call this m. So, let us call this number capital M. So, now what we have is that if x is equal to minus m, then f of x is equal to a naught x to the n times something 1 plus a n minus 1 by a n x inverse plus dot 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 plus a 0 by a n x to the minus n. Well, since a naught is positive, x is negative, this is going to be less than 0, and this third term in parentheses is also positive. So, this is going to be less than 0, if x is equal to m, then f of x is positive. And so, f has opposite signs at the point plus m and minus m. Therefore, there exists x naught between minus m and plus m by the intermediate value theorem. Remember, we have already shown that polynomials are continuous functions. And so, the intermediate value theorem applies, and there is a point, we do not know exactly where it is from this method. However, you could try using our proof of the intermediate value theorem to locate this point. How would you do that? Well, you take this interval minus m to m and keep dividing it into two halves and looking at trying to figure out in which half the root would lie, and you could actually even locate the root using the proof of the intermediate value theorem. But what you do get is that there exists a point x0 strictly between minus m and m such that f of x0 is equal to 0. It is important to note that all the hypotheses in this theorem are important. So, here I should have said has a real root, a real number x0 in R such that f of x naught is 0, and the other important hypothesis is the odd degree. So, now for example, if you take f of x equals x to the power 2m plus 1, where m is any non-negative integer, then this does not have a root because x to the power 2m plus 1 will always be greater than or equal to 0 for every real number x. So, this polynomial has no root. So, this means that it is we need the degree to be odd. I am not saying that polynomials of even degree do not have roots. All I am saying is that we cannot be sure that a polynomial with even degree does not have roots, has a root, and what I am giving you here is for every even degree I am giving you a polynomial that does not have a root. And here is another example. Suppose I take f of x equals x cubed minus 3. This polynomial has only one root, which is the cube root of 3. This polynomial does not have a rational root. Fact is, there is no rational number whose cube is equal to 3. You can try to see why that is true. That is an interesting exercise in its own right. But it does have a real root by the result that we have just proved. It is an odd degree polynomial, so it must have a real root, which says that there is a real number whose cube is 3. The cube root of 3 is a real number, but what you see is that this equation does not have a root for rational numbers. The difference between rational numbers and real numbers is that real numbers satisfy the completeness axiom, which the rational numbers do not. So, completeness is essential for the intermediate value theorem to hold. An interesting variant of the idea of a function taking the value 0 is that of having a fixed point. So, let me call this a fixed point theorem. This again will be a consequence of the intermediate value theorem. So, here is the theorem. Suppose f from the closed interval 0 1 to r is continuous such that f of 0 is positive, f of 1 is less than 1, then there exists a point x naught between 0 and 1 such that x naught is a fixed point for the function f. So, f of x naught is equal to x naught. Let me give you some intuition for this. It's a very intuitive statement. If you think about this function in terms of its graph. So, let us draw the x axis, the y axis, and let us mark off the interval 0 to 1. And now, let us look at the graph of the function f of x equal to x, y equal to x. So, this is just a diagonal line at an angle of 45 degrees, and let us also draw the graph of our function f. So, all we know is that at x equals 0, this function has some positive value. So, something here, it could be even higher up, and at f equals 1, it has some value less than 1. And the graph of this function, well, it's some continuous curve that goes from this point that lies on one side of this diagonal gray line at 45 degrees to the other. And so, it must cross this line at some point. A formal proof using the intermediate value theorem is very simple. Consider the function, you consider an auxiliary function f tilde of x equal to f of x minus x. So, then this condition that f of 0 is greater than 0 says that f tilde 0, well, that is f of 0 minus 0, this must be positive, whereas f tilde of 1 is equal to f of 1 minus 1. But what we know is that f of 1 is less than 1. So, f of 1 minus 1 has to be negative. And this original function f was continuous. So, f of x minus x is also going to be continuous. So, the intermediate value theorem applies. There exists a point x naught between 0 and 1 such that f tilde of x naught is equal to 0. What does that mean in terms of our original function x? It means that f of x naught minus x naught is equal to 0, which is f of x naught equals x naught, which means that x naught is a fixed point for the function f. Okay, here is another interesting application of the intermediate value theorem. So, the statement is that at any given point of time, there exist 2 points on the equator of the earth which have exactly the same temperature. Let us see how this would follow from the intermediate value theorem. So, let us take this circle and think of it as the equator of the earth, and on this equator we have 2 cities. For example, we have Singapore, right, which is right on the equator, and we have Bogota somewhere on the other side of the earth, which is also, well, pretty close to the equator. Okay, and right now I looked it up, the temperature at Singapore is 31 degrees Celsius, and this temperature at Bogota, which is at quite an altitude, is 13 degrees Celsius. So, the intermediate value theorem, well, I think it is a reasonable assumption that temperature along the equator of the earth is a continuous function. And so, the intermediate value theorem tells us that there must be a point somewhere on this arc between Bogota and Singapore where the temperature is going to be 15 degrees Celsius, and another point on the other arc, we do not know exactly where the temperature is also 15 degrees Celsius. There was no reason for me to pick 15 degrees Celsius, but in fact you could have picked any temperature between 13 degrees Celsius and 31 degrees Celsius, and you would get 2 points on the equator which have the same temperature. So, in fact, you have seen that there are lots of points, pairs of points on the equator which have the same temperature, but I can strengthen the statement a little further. I can say that there are actually 2 diametrically opposite points. on the equator where the temperature is the same. So, we will just modify this argument a little bit, we will still be using the intermediate value theorem. So, here is my equator, and what I am going to do is, okay, so let us take the center point here, and let us draw the x axis. So, this is the x axis, and here is a line drawn at angle theta to the x axis. So, in this case the way I have drawn it, this angle theta is a negative angle, let us say in radians, and on this other diameter at an angle theta I have 2 points a theta and b theta. Let us define a function f theta to be the difference between the temperatures at a theta and b theta. Now, let us look at f of 0. So, this is going to be the value of the temperature at this point here, A0 and B0. Now, if f0 is equal to 0, then we are done, because we found 2 points A0 and B0 which are diagonally opposite and have the same temperature, because this saying f0 is 0 is just saying that T of A0 is equal to T of B0. So, then we are done. Otherwise, let us look at f0, say it is positive, we can deal with the negative case similarly. If f0 is positive, let us look at f of the angle pi. So, what is happening is that we have just taken this diameter and rotated it by an angle of pi. So, that is all the way to 180 degrees. And what happens is that A0 is, A and B get interchanged. So, A pi is over here and B pi is over here. So, what we have is f pi is going to be less than 0. Similarly, if f of 0 is less than 0, then f of pi is going to be greater than 0, simply because f of pi is the negative of f of 0. And so, by the intermediate value theorem, there exists an angle theta between 0 and pi such that f of theta is equal to 0. But that just means that the temperature at a theta is equal to the temperature at b theta. And so, we found two diametrically opposite points on the equator which have exactly the same temperature.